Okay, so this is a multivariable linear regression problem. Okay, so then how can we solve this linear regression problem in a multivariable setting? Okay, so as we discussed previous slide, we can define the models or the mapping function of this multi-feature linear regression problem as like this, with the variable parameter vector w with the input variable x, like this. So this is the parameter vector consisting of w0, w1 through the wn, like this. So what we want to do is to choose or to estimate this parameter w that minimize the ground truth, the output with the estimated output with this mapping function, right? It is exactly same with the single variable regression problem. So we also need the cost function looks like this. Let's say we want to use this MSE loss function like this, that is defined with a scale with the difference between ground truth with the estimated one, right? So this is a MSE loss function. If you don't remember this, please go back to the last week lecture, right? So anyway, we can define the cost function like this. Yeah, so this is a gradient descent procedure comparing to the single variable case and the multivariable case. Single variable case, multivariable case. Okay, so in the single variable case, we need to find the only two variable, w0 and w1, right? So how can I estimate this? First we can find the derivative of this loss function with the w0 and multiply the learning rate alpha and move the previous previous w0 to the next w0, right? So this is the one step for updating the alpha 0, and for the w0, and for the w1 the same step I'm using. So first of all, from the previous w1 we multiply the learning rate with the gradient of the loss function, right? So this is the one procedure of the gradient descent for single variable. Now we have to find the multiple variable, right? Multiple parameter variable. So it means that comparing to this one, we need a wj, right? So wj means the j is start from 0, right? 0, 1 through the n, right? So it means that to repeat or to iterate this procedure, we need some kind of for loop, right? Here we need a for loop, right? You know what is the for loop or the while loop, right? In implementing this gradient descent in your computer, but in this single step, we also need to compute the wj. So it means that we need another for loop or while loop to compute these values per each samples or each parameter variable. Okay, so anyway, so what we want to do is from the previous parameter wj, we want to compute the derivative of the loss function with respect to the wj and multiply this value by alpha, and then we can compute new wj. So it will be the next current wj in the iterative solution. Okay, so what was that? What was the LW? LW was looks like this, right? So this function should be like this. So this LW can be represented in a MSE loss function like this, right? Right. Then how can we compute the derivative of this loss function with respect to the wj? Right? How can we represent this? What was that? What was that? It was what? It was w0 x1 x0 plus w1 x1 plus w2 x2 through the wn xn, right? So okay, let's do w0 first. What is that? What is the derivative of this one with respect to the w0? First of all, in this linear equation, this term only related to the w0, right? So derivative of this term will be x0, right? What if the w1, we choose the w1, this term related to this term only, right? So it should be x1, right? Right? So I guess you already know the chain rules to compute the derivative of this whole term, right? Here we just define the derivative of this term, but in this equation we have to compute the derivative of whole this term. So what do we have to do? First of all, we have to compute the derivative of this term first. So what is that? These two should be here, right? Right? And it will be just the first order, and the derivative of this term like this should be here. Okay? By chain rule. Okay? Please do it yourself by your hand, because most of you, I think all of you already learned this. What is the chain rule and how can we compute the derivative of this function, right? So please do it yourself. Anyway, so finally the one step compute function looks like this. So the previous, the wj minus alpha, learning rate alpha, times with some constant. Actually it's just a constant value, right? So if you find another textbook, so this loss function start from the 2 over n. So it might be eliminated this constant 2, right? But actually it's not important, because this is just cost function. So main the core part to update this parameter wj is here, right? So actually the constant function is it's not important, but as you can see here, let's see. Okay. As you can see here, we define the alpha is the learning rate, right? Actually, alpha is also constant value, isn't it? Then what does that mean? Alpha times 2 over n is also constant, right? So what does that mean? When we define this learning rate, we also consider this parameter, right? If you didn't implement this normalized term, then learning rate, we can adjust the learning rate alpha over n. Okay, so because this is only constant term, okay. Anyway, so this is one step of the gradient descent for multiple features. Okay. Okay, the last part of the first section of our today's class. This is a normal equation. So what is normal equation? Okay, let's see the example. Okay, when we use the gradient descent, we just assume that the cost function looks like this, right? Looks like this. Let's see the example. Where is that? Where is, yeah. Okay, let's see this one. Yeah, this is a cost function of the linear regression problem, right? So the cost function looks like this. It means that if we just start from the arbitrary point, the each step just follow this line, right? But actually, in the most linear application that use the machine learning, the cost function is non-linear. Looks like this or looks like this. So actually, in these cases, it's really hard to find the global or the local optimal just using the original gradient descent. So there are several kinds of the variant of the gradient descent called the SGD or something like this. So actually, if you want to use the gradient descent algorithm from some kinds of library, even for deep learning, there are well-defined and well implemented gradient descent algorithms such as the SGD or the Adam solver, something like this. Because in most cases the cost function are not convex. Looks like this. Okay. Anyway, what if the cost function looks like this? Just convex case. In this case, actually it's very rare case. Anyway, if the cost function looks like this, we can compute the optimal of the cost function analytically. Okay, what does that mean? Okay, so linear regression using the mean squared error cost function. What we have done so far, right? In this case, we can solve the solution by solving the linear system, which is called the normal equation. What does that mean? Let's see the example. Okay, so first of all, let's think about we only have the single parameter w, okay, and the loss function looks like this with the MSE cost function, okay. Then what was that? What is that? It's just w times xn, right? Because we only consider a single variable. Then if we expand this term with the summation here, anyway, this function can be represented look like this, right? With the arbitrary number of a, b, c, right? Anyway, this is the second order equation. Then what does that mean? The shape of this second order equation should be looks like this. Looks like this, right? Yeah. Okay, where is that? Yeah. So, in this case, this point will be what? Global optimum. In this case, this will be the global optimum. Then it is equal to also local optimum. What does that mean? If the loss function looks like this, the local optimum is exactly equal to the global optimum. Okay. Anyway, so this is a global optimum that we want to solve for this linear system and this machine learning problem. Then how can we solve this point? How can we get this? We already know that we already learned this in the middle school and high school, right? How can we solve this? Yeah, let's see the several example right here. If we compute the gradient of this function, the gradient will be looks like this. If we compute the gradient in here, it will be looks like this. If we compute it here, it looks like this. So what does that mean? In the global optimum point, the gradient of this loss function should be 0, right? Because the slope of this okay, let's use the blur. Yeah, slope of the gradient at this point is 0, right? So it's like this. Because this loss function is the function of the w, right? So if we just estimate the gradient of the loss of w with respect to the w, will be the what? Linear equation, right? Why? Let's think about this. Okay, so when we compute the gradient like this, what is that? 2aw plus b, something like this, right? So this is the kind of the linear equation. Then what does that mean? What does that mean? So how can I solve? Because this is a linear term and should be equal 0. It means that this equation represent the some set of linear equation. What does that mean? This is the also called linear system. I'll let you know in the first lecture of this course. So please go back to the slide if you don't understand what is a linear system. Anyway, so it will be the linear system. So what does that mean? To estimate this parameter w can be reformulated using the some linear equation. It means that solving for the parameter w will be solving the linear system. Okay. So let's do this in a general formulation. Okay. What you want to do is to find the parameter w is equal to w0, w1 through the wn. So this parameter vector is the size of the n plus 1 times 1. What does that mean? w0 is w1 like this. Okay. So it consists of the n plus 1 row with the 1 column. Okay. And we also have the loss function looks like this with the MSE loss. Okay. So and we also know what is this loss function, this mapping function means, right? What's that? W transpose x n, right? So this was a loss function, and right. And then what do you want to do? We want to find this parameter w. How can we solve this? Similar to this one, we can just to compute the gradient of this loss function with respect to each parameter of this one. Okay, wj. Okay, for every j. So what does that mean? If we just compute the w0 it makes some linear equation 1, right? And if we compute another equation, it introduce another linear equation, right? And if we compute the gradient of this loss function with respect to the n, will generate another linear equation n. Okay. Let's say this is linear equation 0, 1, n. Then what does that mean? The solution of this linear system. Okay, let's say LE, linear system. This linear system 0, linear system 1 through the linear equation n. Here it is. What does that mean? The solution of this linear system this linear system should satisfy each equation, right? Then how can you solve this? there are several kinds of methods to solve this linear system, right? For example, I guess you already know the Gauss elimination, right? Or there are several kinds of methods to solve this linear system, but there is a more analytical way to solve that linear system. It's called the linear scale. Okay, so what does that mean? Okay, let's see the previous example here. This example is to estimate the house price from the several kinds of input variable. Let's say x1, x2, x3, x4, and this is the samples, like x1, x2. Let's say we have the 4 kinds of sample, and then we can represent this input variable looks like this. What does that mean? This is the size of the feature. So it will be here. The number of bedroom will be here, here, here. And what does that mean? At the beginning, we define the x0 is equal to 1 for every samples. So x is looks like this, and y is the output variable y looks like this, and then in this case we can generally represent the xi. Xi means this column, okay? Because the R is n plus 1. Wait, use in this case, no, it's not.